Hi there. Welcome to the lecture on using stochastic actor-oriented models to estimate change in two-mode networks. So I'm Dr. David Schaefer, and I'll be walking you through this today. So just to give you a brief overview of what this lecture will cover, I'm going to start off talking about what is a two-mode network, make sure we're on the same page. And then I'm going to talk about Zaum or Siena model specification and assumptions when modeling change in two-mode networks. I'm going to assume that you've already know something about Siena models, that you've watched a previous lecture or have estimated them. So I'm going to be, again, assuming you're coming in with some working knowledge and won't be covering all the basics of the model itself, mainly just how things are different with the two-mode network. I'll spend some time talking about the different kinds of effects that you can model. In other words, the selection mechanisms that actors use to make choices of events. I'll talk about what the data structure should look like and then how we set up the model. And then I'll go through some results from a model that has been estimated to the data that you have for the lab section of this, and then point out a few things in the R script. Okay. All right, so a two-mode network is defined by there being two sets of nodes. Okay, so we have two sets, and then we have relationships only between these two sets. We don't necessarily have relationships within either set. Now, there might be relations within one set, and that would be a separate one-mode network that can be examined alongside the two-mode network, but a strict two-mode network does not have ties within either set. Now, for this lecture, I'm going to talk about these two modes as actors and as foci, and that the tie between actors and foci represent a membership. Now, the foci can be lots of different things. Okay, Feld's famous quote from his 1981 paper, they could be persons, places, social positions, activities, groups. He's really talking about how foci are opportunities for people to meet. But as we'll see when we're modeling two-mode networks over time, these foci, they might also be a source. Actors might learn from one another which foci to join. So they're kind of an endogenous process. We're not taking foci membership as granted, but we can predict which foci actors belong to. Okay, so here's an example of a two-mode network. This is just a simple one where we have two nodes designated by their mode. And in this case, actors are circles and the foci are diamonds. This could be authors and the texts that they write, where co-authors are people who have written on the same text. This could be students, and students have courses in common, so students enroll in courses, and thus students are connected to courses, multiple students are connected to a course, and multiple courses are connected to one student. It could be people and events. So the famous Southern Women data looked at a group of women and the events that they attended throughout the year. Okay, now notice again, each of these sets or modes, there's not necessarily relations between them that we're looking at. So when we're looking at the attendance relation, we're looking at people attending events, not how the people themselves are connected, and not any association between events. Okay, now shifting to how to model change in a two-mode network over time with a Zaum, I want to point out that a Zaum is this is a special case of a one-mode Zaum. So actually when modeling this network, when working with our Siena, the machinery behind the scenes is really the same. The big difference is that with a two-mode network, there are constraints on who the actors are. Okay, so actors are divided into two groups, actors and foci. And only that first set, actors, can actually make decisions and send ties. The foci do not send ties. They're simply the recipients of ties. So there's some constraints within that machinery. There's also a constraint that actors don't have ties to one another and foci don't have ties to one another. So this has consequences for the kinds of things that we model, the kinds of effects we model. So within two-mode networks, there are no triangles. So triad closure is impossible. So any effects that involve triads, if it's triad closure, then those are no longer relevant. Okay, homophily is, as we think about it in terms of two actors being connected because they're similar, well, that needs to be reconceptualized when connections are between two different modes. So again, thinking about the Southern women and events, what would homophily mean for when one node is a woman and one node is a gathering, a party? That doesn't have the same meaning. So we need to reconceptualize what that means. We might have indirect homophily, which is something I'll talk about, where women join events with other people like themselves. We can have indirect homophily that way, or we might have some kind of match between a person's characteristics and something about the event themselves. Okay. Other than a few kind of constraints on which effects are and which ties are possible, many of the model features you understand from a one-mode specification carry over. So we're going to condition on a two-mode network observed at time one, and then we're going to model subsequent changes across time. Okay, we're going to have a rate function that models when changes occur, and objective functions that determine which change is made, if any. And then our change decisions are going to be informed by the current network structure, actor attributes, or attributes of foci. Okay. Several assumptions are shared with the standard ZALM, but are important to keep in mind. First of all, relations are relatively enduring states. We're calling these memberships to kind of signify that these are relatively enduring. They're not instantaneous events. Okay, so if we're thinking about a communication network where we're looking at messages sent or other kinds of actions that have a kind of instantaneous nature, we don't want to use a two-mode ZALM unless we do some kind of aggregation over time and think of these relations as representing some other kind of latent state that does have this more enduring nature. Change decisions are going to be modeled from the actor's perspective. So in the two-mode ZALM, actors send ties to foci. Foci are just there to receive ties. They don't do anything themselves, although they can have attributes that actors use to make decisions about which foci to send a tie to. Actors change up to one tie in a given microstep. So an actor might join a focus, might leave a focus that they're already a member of, or make no change to their sets of memberships. Now, actors can't leave one focus and join another at the same time, right? That's part of this being a Markov process, and change is one tie at a time. So when thinking about modeling your two-mode network, think about the nature of change, and is it possible for actors to belong to no foci and belong to multiple foci, which is needed if actors are going to change from one foci to another. Okay, that is, an actor might at one point belong to no foci, having left one foci and has not yet joined another, or an actor might belong to two foci if they belong to one, join another, and then leave the first. Okay. Actors also make changes sequentially, so they are not joining foci kind of en masse together. Actors join a foci one at a time, so there's not coordinated action to, let's, for instance, among a group of friends to join a particular club or something together. And then lastly, the set of actors and foci are exogenous, okay? And this is important because we're not talking about events or foci that actors create. We can't model actors coming together and creating a new foci, okay? That would be wonderful if we could, and with some, maybe with relational event models, we're kind of moving to being able to do that. But with the Zaum, we're taking the set of actors and the foci is both that set of possible actors and foci. That set is already pre-existing. Now that said, actors can come and go, and foci can come and go, and we can model changes in those sets or allow changes in those sets over time, just as we can with the one-mode Siena model. Okay. All right, so I want to talk briefly about some of the different kinds of things that we might want to model, right? Some of the different kinds of changes. Okay, so we might be interested in, are there differences across actors and how many foci they join? Are some people joiners? Other people are not. So we can model that both with actor degree distribution, but also we can get at heterogeneity among actors if we have attributes that we think might lead some actors to be more sociable than others. Okay. For example, we'll be looking at some data on adolescence and activities, school-based activities. And one of the hypotheses or findings really from the literature is that higher SES adolescents with higher socioeconomic status tend to belong to more activities. So that's something we could model as an actor attribute. Okay, there might be differences in foci and how many members they have. So are some foci more popular than others? Okay, we can model the degree distribution of different foci as well as their attributes if we have some hypotheses about what might make foci more attractive than others. We might have questions about, do certain types of actors prefer or avoid certain types of foci? Okay, so we can kind of look at interactions between actor attributes and foci attributes, or interactions between actor kind of sociality and foci popularity. We can look at interactions to try to specify kind of those niches. Do certain kind of activities fill certain kind of niches and reach certain kinds of or appeal to certain kinds of people. I mentioned earlier hemophilia, right? Actors might prefer foci with members like oneself. Okay, so we can model that if we have an actor attribute, and then actors are indirectly connected to others through a two-path, right? An actor is connected to a foci, other actors are connected to a foci. So by looking at those two paths combined with actor attributes, we can model if if there's this kind of self-sorting into foci with similar members. We might wonder if co-members influence one another's foci memberships. Okay, so if I'm in an activity, are the people I learn about activities from my fellow members, do I then have a greater likelihood of joining activities that my co-members belong to? Okay, so that's a kind of a force cycle. We'll see that shortly. And then it could be that other relations influence foci membership, or vice versa. Okay, so we might have multiplex effects. So I mentioned earlier, we might have a one-mode network associated with one of the modes. So if we're looking at students and activities, there are likely to be friendships among students that are important, and being friends, having a tie in a one-mode network might make belonging to the same foci, more likely. So we can test for that kind of peer influence or friendship influence on foci membership, as well as if foci membership predicts friendship, such as Feld predicted. Okay. All right. So I'm going to present some common kinds of effects we might be interested in. I'm not going to go into depth on all of these, but I want you to see kind of how these things are instantiated. Okay, so I mentioned earlier we have actor attributes that certain types of actors, and here in this configuration, the shading means the actor attribute is salient. Okay, so we have the circle representing the actor with a certain attribute. And then here is a foci or focus. We're not interested in its attribute at the moment. And what we're interested in is, are actors with a certain attribute over time more likely to add ties to a focus? Okay, so this gets at sociability, whether some types of actors are more sociable or more likely to be a joiner. This is the formula used to calculate the effect in the Siena manual. If you're going to be modeling with Siena, you need to get fluent in how to interpret these, spend a lot of time, any kind of understanding, how to specify particular effects, particular mechanisms that you're interested in. It's going to depend on finding effects that with Siena, effects are pre-existing. It's challenging to create one's own, but though it is possible. And so finding effects that align with your hypothesis is an essential part of the process. So this is the ego X effect, and the V sub I is a behavior or an attribute, an exogenous attribute for actor I. And XI plus is looking at I's out degree in the network. So their product. Okay. So I want to mention that. I also want to mention I put the short name in here for the effect, as well as the code from the R script that sets up these effects. In this case, we're going to be modeling if socioeconomic status predicts membership, and then we're going to be modeling if females versus males are more likely to or less likely to belong to foci. So differences in actor gender. Okay. All right, so we have actor attributes. We can also look at attributes of foci. And in this case, are foci with a particular attribute more likely to be selected in general? So are some foci more popular? And here we'll be looking at, in the case of our TwoMode data, we have activities, school-based activities that can be divided into different types. There's sports, there's leadership activities, art activities, and special interest. And so we'll be testing if any of those differ from, in this case, we're omitting the sport category from our analysis. So do these differ in popularity from sports? Okay, just as with your one mode Siena model, it's important to control for the degree distributions. So here we have effects for the foci degree distribution. Okay, so do foci, in this case, a positive effect would mean foci with more incoming ties tend to receive more incoming ties over time. And then we have our out degree activity, which is our actors with more outgoing ties more likely to add a tie across time. Co-member influence. So here we have, sorry about that. Here we have two actors who belong to the same foci at time one. One actor also belongs to a second foci. And then at time two, the second actor joins that same foci. Okay, so here we have a 4 cycle, but with directed ties set up set up accordingly. And again, you can see how it is calculated here, as well as the script to add that to your model. Okay. The indirect hemophilia effect. Okay, here what we're doing is we have an actor with a given attribute is a member of a foci at time 1, and then at time 2, a different actor with that same attribute joins that foci. Okay, so this indirect hemophilia via the foci is what we're capturing. And so we're representing that with, again, the formula here. If you're not familiar with this latter half here, what we're looking at is, does the attribute of actor I match the attribute of actor H? So one actor is I, one actor is H. Do those match? If they do, this is a 1. If they don't, this is a 0. Okay, so if they don't match, this whole thing turns into 0. If they do match, then this latter half is a 1, and we're simply looking at, is there a tie from I to J, with J being the focus? Is there a tie from I to J? And is there a tie from H to J? Okay, and if so, that contributes 1 to this statistic. So we set this up with the same X in pop effect, and then specify the attribute itself. Okay, and here it's worth mentioning this because we're looking at whether or not two actors are identical. This works best with categorical measures, where being identical is more important. If you have continuous measures, there's other effects that would be appropriate. Okay. Complementarity is another form of hemophilia, potentially, or it could be kind of getting at the concept of niches. So here what we're doing is we have an actor and a foci, each have an attribute. Remember though, they're not the same attributes because these are different modes. Okay, so they each have an attribute, and does having a particular value on that attribute for actors lead them to select foci with a particular value. Okay. And so in our data, what we're doing is looking at, for instance, do actors vary in socioeconomic status? And so do higher socioeconomic status actors, are they more likely to join leadership activities, art activities, and special interest activities compared to lower SES adolescents? Okay. All right, so this is an interaction that we're creating. We're using the include interaction function to set up the effect. Now, if you've done some Siena modeling, you might be thinking, well, there is an ego X alt X effect. Why don't we just use that? But if you go and look at how that effect is constructed, you'll notice that the ego X and alt X effect rely on ego and alter. It looks at the same attribute for each. And here, because ego and alter are from different modes, their attributes will differ. So we're setting this up by creating an interaction. Okay. A second form of complementarity, we could look at other interactions between ego attributes and alter attributes. Here we're looking at ego's attribute in terms of, in this case, we're looking at ego's gender, and alters position, the foci's position within the network. Okay, so are certain kinds of actors more drawn to foci that are more popular, or drawn to larger foci? Okay, so we can, again, this is an actor level attribute and a foci level position or degree in this case. We could switch things around and use ego's position and alters attributes. We could think of maybe some different kinds of combinations, but these are all ways of getting at, do certain types of actors and certain types of foci, are those more likely to match, so to speak, or have a heightened likelihood of there being a tie. All right, now I want to take a few moments to talk about this issue that arises with our data, but there will be other. This isn't isolated. With our data, which is high school activities, there are some activities that are gender specific. They target a specific gender, and for the most part, these are sports. There are, there's a men's volleyball team, and then there's a women's volleyball team. Or in high schools, they often call them boys teams and girls teams. Same with soccer, same with most other sports. And so we want to account for this kind of exogenous constraint within our data. And so I should mention, one thing we could do is we could put structural zeros in our network. And simply make it impossible for boys to join girl activities and for girls to join boy activities. That's one possibility. But in actually looking at our data, we realized, there are a few girls in boys activities. There are a few boys in girls activities. Not a lot, and not in every activity, but there are some violations of this. It's not a strict rule. And so we wanted to leave open this possibility that these kinds of memberships do occur. And so we're going to make this probabilistic. It's unlikely for boys to join girl teams, but we're going to let the model tell us how unlikely it is. Okay, so because we know that, right, we know with survey data, it could be error, right, that leads to seeing boys and girls activities. But because we gathered this data and we know it's not an error, it's just a feature of high school activities these days. So we want to account for that. All right, so here's actually our mixing matrix. Okay, so we have actor gender as the rows and the foci kind of gender specificity as the columns. Okay, and so we don't, in this set, we don't have any males in girl foci, but we do have one girl within a boy foci. And then we have mixed foci that draw from both genders. Okay. Okay, so this is what actually if we're modeling the two-mode network and looking at the rates of male and female membership and the rates of popularity of different activities, these are actually the target statistics that we're trying to, the model is trying to kind of recreate. Okay, so this is what we will be modeling is these counts here. Now, when we model, we can model the marginal totals of this table, right? We could specify these as our counts and model these, or we could model the specific cells themselves, okay, using interactions between actor gender and the foci gender. What I would point out is we have 6 cells here with independent information. We can have up to 5 effects that model this, and with the reference category. Okay, so we have to keep that in mind. If you've done log linear modeling, then the idea is similar in that you want to think about how your modeling of marginals represents certain cells, and you want to make sure to not use up all your cells and to leave one cell unmodeled as the reference category when for instance, with Siena models, we have an out degree in the model to control for the overall probability of a tie. And so that's going to capture the cell that we leave unmodeled. Okay, so let's look at what that looks like here. Okay, we're going to add an ego X and for females. Okay, so that's going to capture this total here, how many females are in activities. Okay, we're going to have an alter effect for girl foci. All right, and that will model this total here. We'll have an alter effect for boy foci, which will model this total here. Okay, so that leaves our reference category here being males in mixed gender foci. Okay, that's a reasonable place to start. We're getting at differences in actors based on gender, and we're getting at differences in are some kinds of activities more popular than others. But that doesn't get at this right here. Okay, so we're not capturing this interaction here, right? Where boys don't join girls' activities and girls, for the most part, don't join boys' activities. So to do this, we need to specify an interaction. Okay, so we're going to have one interaction that's a male actor by girl foci. Okay, we expect that to be to have a negative estimated coefficient. And then we have another interaction that's female actors by boy foci, which we also expect to be negative, because these are far less likely than we would expect by chance. Okay, so when we add these, we count up, we have 5 effects. Okay, that's the maximum we can have. We've left one cell unmodeled. So we will be perfectly modeling this table here. Okay. Okay. All right. So to do this, we're using this the same effect we talked about earlier, the interaction between ego and alter attributes. In this case, the one interaction is a male ego and a girl foci as the alter. The other is the female actor with the boy foci as the alter. Okay. All right. So now I want to talk about if we have multiplex, we have multiple networks. Okay, and so here we're talking about bringing a friendship network and modeling friendship as another evolving network over time. So we've got friendship evolving and we have memberships evolving over time. And so if we're interested in whether friendships drive membership, that's a form of peer influence. What we're talking about is a situation where at time 1 in our one mode network, we have 2 actors who are connected. One actor belongs to a foci, and then at time 2, the other actor joins that same foci. Okay, and so that's modeled. We model it with the 2 effect here. I should mention in a paper I'll be talking about later, we were interested in this effect, but we had a network that we wanted to use to predict this kind of influence, but that network, we did not want it to be endogenous. We did not want it to co-evolve. We wanted to treat it as a static kind of exogenous network. And to do that, we ended up bringing that one mode network in as an endogenous network, but using the trick that Snyders and Steglich did in their simulation paper, where we only changed one tie in that network. And so it's basically the same network. And then we fixed the rate parameter at a low number. Maybe it might have even been 0. I'd have to check. So basically that network was brought in and was called an endogenous network, but it really did not change over time. And all the change happened in the two-mode network. So it is possible to bring in kind of static networks as a predictor of along these lines. But there's some kind of creative model specification needed to do that. All right, now there, you might also be interested in modeling the foci effect on the one-mode network. Okay, so here the question is, do members of the same foci form a tie in the one-mode network? And so we have two actors who belong to the same foci, and then at time 2, they form their own tie in the one-mode network. Okay. All right, so it's really the inverse of the process on the previous slide. And so this is a way of kind of getting at selection versus influence in terms of foci membership. Okay, is foci membership a source of friendship, or is friendship a source of foci membership? We can start to parse that out. Okay. All right, now let's talk about what's needed to model change in a two-mode network. Okay. Really, all you need is a two-mode network modeled at 2 points in time. Okay, that's it. You don't need anything else. The two networks should each be represented as a matrix with actors as rows and foci as columns. And just as with your regular Siena model, each time point should have the same dimensions. So you should have the same actors at each time point and the same foci at each time point. Okay. Now you could bring in lots of other kinds of data. You could bring in a one-mode actor by actor network to serve as some kind of dependent or network if you want to model coevolution of two-mode and one-mode networks. You can bring in actor covariates. We'll talk about exogenous covariates, but you could also have endogenously changing behaviors as actor covariates. You could have focus covariates. Those are exogenous because foci are passive entities, so they can't change their attributes endogenously, but their own attributes could change exogenously over time. We could also bring in a dyadic covariate as a rectangular matrix, having the same dimensions as our two-mode network. Okay. So when we get to estimation, I want to emphasize the importance, first of all, of examining your data, because oftentimes there are just some weird patterns or idiosyncrasies that you want to take into account. Such is the case for in our case, this gender specificity of activities was really prevented certain actors from joining certain foci, and it's something we need to take into account to get a reasonably fitting model. And there might be some other things as well. So really, there are things you can anticipate being in the data, but there are other things you may not anticipate. And so kind of doing a little detective work beforehand to understand your data is vital. So I also want to emphasize looking at the print01 report function within our Siena. Okay, once you put your data together and turn it into a Siena object, the print01 report provides a summary of that Siena object. And so this is what Siena thinks your data are. These are the dependent networks, the networks that will be set up to be modeled. These are exogenous, either networks or attributes, and some descriptives on those. So this is a good way to check that what you think you're bringing in as data and how you think that data is coded, that looks the way it should. It's much better to catch something here versus setting up and running a model that takes a couple of days and doesn't fit, and you don't know why, and then you realize, oh, Siena treated this measure differently than I had meant for it to do. Okay. The lab script has some comments in there about some points along the way regarding estimation and convergence. Again, this step is largely the same as modeling a one-mode network, so I'm not gonna dwell on those similarities. Okay, here's the data we're modeling at the two time points. The red are students in a high school, and the blue are the activities they joined. Here's the degree distribution. Okay, what's good to know here is that in terms of actor out degree, you can't see it, but there are a number of actors who don't belong to any activities. And so that's important to keep in mind. We might need an isolates effect to account for that, although the distribution for degree is fairly linear, so that may not be necessary. In terms of foci on the right here, we see most foci are quite small, with a handful that get larger, so there is a skewed distribution. We might need a nonlinear popularity term to account for that. Also, you can't see here, but all foci have at least some members in them. Okay, so we don't need to be concerned about isolated foci. Here's some snippets from the Print 01 report. So the script sets up the data in two ways. The first way is just a two-mode network. And the Print 01 report here shows that we've got a membership network that's bipartite. That's a two-mode, let's see, bipartite. A two-mode is a special case of a bipartite network. Bipartite simply means you have two sets of actors or two sets of nodes, and all of the ties are between the sets, none within the sets, which could be a two-mode network, or you might have a one-mode network. But that's the structure. And we name those students, and there are 223 of them, and we name the others foci, and there's 32 of them. You'll see that in the script. Okay. The second is a second version of the data that we set up that also brought in a friendship network among the students, which is one mode, and here you can again see these are the students. We also brought in actor covariates, 11 different actor covariates. Now, these aren't differentiated between students and foci in the Print 01 report. So we're having to keep those straight ourselves. All right, we also get a number of missing cases. Good to keep in mind, and again, check, is this the rate of missingness that I expected, or is something goofy potentially happening? We also have our covariate information, including whether or not effects are centered, which will be vital to know and take into account when we're interpreting, if we want to make any kind of predictions across different kinds of scenarios. Okay. All right, we've got reports of how many ties there are, density, missing ties, and then change over time. And again, we want to pay attention to the Jacquard, which is the proportion of ties observed at either point in time. How many of those are constant across time? We ideally want that to be greater than 0.3 or 30%. Here we've got we well exceed that. So we've got sufficient stability to be able to model the network. We don't want that so high that nothing changes. That would be a problem in the other direction, but we do want, again, a certain level of stability in our network. Okay. All right. The first part of the script runs a really simple model that just checks for this indirect homophily, right? Do actors choose foci with members who are similar to oneself? So we're going to estimate simple models that only include this same X in pop. Okay, so we're not including any other controls. We have to include out degree, but we don't have anything else in there. Now, this I want to be really clear on what this model specification tells us. What this tells us is there a pattern of indirect homophily over time? In other words, is there a tendency, if we're kind of watching the network, is there a tendency for actors to be joining foci or remaining in foci when there are more members who share their attribute? Okay, is there this pattern? We're not trying to determine the cause of this pattern. Okay, we're just trying to see, is this pattern there? Okay, and for all three of these, race, gender, and socioeconomic status, we do see significant effects, right? The estimate is more than twice its standard error, okay, for each of these. So we do see a significant effect in the positive direction. So there is a pattern whereby people of the same race, the same gender, and the same socioeconomic status tend to end up, in the same activities, at least at greater than chance rates. We're not saying we have totally homogeneous activities, but we are seeing kind of this sorting into activities at greater than chance rates. So that could be due to some kind of preference on the part of actors, or it could be due to many other kinds of selection processes. And so that's where the other effects we've talked about come into play. We'll want to see, is that what's driving this, or is this a product of some other kind of selection process? Okay. All right. So we do see this homophily. Now let's look at some more fully developed models. And in fact, these are probably too fully developed. So I'm going to walk through a model that comes from the script. It's the last model estimated in the script that has way too many effects. But the goal is to show how one would specify and interpret these effects. In real practice, you would be better to take a more of a forward-fitting model strategy and really focus on effects that are of theoretical interest and not include every action you can just because maybe it has an effect, but using judicious use of score tests to try to guide one's model development. Okay. I want to point out here that in this model specification, these are the three indirect homophily effects. Two of them are negative, and the third is positive, but not significant. The negative effects actually indicate that people are joining activities with members who are dissimilar on that attribute. So in terms of race, it's not significant, not far, but it's the negative sign would be that people are drawn to activities with members of a race other than their own, and the same for gender, that people are drawn to activities with co-members of a gender other than their own. So keep in mind, this is net of other effects in the model. So this gender effect is net of the effects we talked about earlier that control for the kind of the gender-specific activities. Okay, so those are primarily gender-specific, but so here we're getting more of the mixed gender effects. Okay, so I walk through some different effects here and highlight their interpretations. I'm not going to focus on all of these. You can read through this. I do want to point out, though, when we are including interactions, such as this actor gender by foci, gender specificity, when it comes to interpretation, anything with interactions gets complicated. Okay, and the go-to way to reduce that complexity and make it understandable is to calculate predicted values. Okay, so in the case of Siena models, that is calculating ego-alter selection or ego-alter influence tables. So here we have an ego-alter selection table. based on actor gender and the alter specificity. Okay, what we've really done is, this is our objective function, okay, and we've pulled out those effects that are directly relevant to either ego's gender or alter specificity or their interaction. Okay, all other effects we can hold constant while we're manipulating these. Okay, and so we're thinking here, okay, hypothetically, if a male actor chooses a girl foci, what's the predicted contribution to the objective function for that selection? What if the male actor joins a boy foci? Okay, or what if the male actor joins a mixed foci, right? How do these differ? And so we're calculating, again, we're plugging in for each of these the value of our attributes. Okay, this is easy because these are dummy variables that are coded 0, 1, and we didn't center them. Okay, so our ego female is coded 1 for girls, 0 for boys. In the case of a male, this is 0. Okay, our girl foci is coded 1 for girl foci, 0 otherwise. Okay, so for a male joining a girl foci, this would be a 1 times 3.26 becomes this number right here. Okay, in this situation, boy foci would be 0. Okay, so that's coded 0. That evaluates to 0. A male joining a girl foci, well, we're talking about a male, but we're talking about a girl foci, so that brings in our estimated coefficient of -5. I should mention these are all the estimated coefficients from below. Our coefficient of -5 comes in, and so we subtract that. Okay, and then the interaction between female and girl foci would be down below, so that's not relevant. So that's where our predicted contribution comes from. And so we're making our predicted contribution for every combination of actor gender and foci gender to get these contributions. Okay, and then we can look across. Numbers that are higher are things that are more likely to occur. Numbers that are lower are less likely to occur. So males are more likely to join boy foci and less likely to join girl foci, with mixed foci kind of in the middle. Okay, for girls, they are most likely to join girl foci and then kind of less likely to join boy foci or mixed foci. Okay, another way to think about that is we can make comparisons kind of within actor. Okay, so for a boy, we could make the comparison of, well, do I join a boy foci or a mixed foci? Okay, and the difference works out to be the difference between these contributions here are in log odd scale. So if we take their difference and exponentiate that, then we get the difference in odds. Okay, so here boys are 31. Let's see. Did I get that right? I think this difference is 31 times. So for boys, the difference is 31. Boys are 31 times more likely to join a boy foci compared to a mixed gender foci. And for girls, joining a girl-specific foci, the odds are 26 times greater relative to the odds of joining a mixed foci. These numbers are huge, right? Part of that is this model is small and it's a small network and an oversaturated model. You know, those differences are huge, but it does tell you that, right, these are more likely and these are less likely, with the mixed gender being somewhere in between. Okay. All right, last couple effects I do want to mention is we've got the last effect in the membership function is predicting whether friendship affects membership. Okay, so this friendship to agreement means if we are friends, do we agree on which foci, right? Do we select the same foci? And the positive estimate means that yes, actors are more likely to belong to foci that their friends belong to. Okay, so that's evidence of peer influence on membership. Okay, here we have the friendship function. This should look quite familiar. If you've modeled one-mode networks, you're familiar with these effects. So I won't dwell on them. The one I do want to point out is the multiplex effect, where we are predicting friendship based on being in the same foci. And we do see a positive significant effect here. So co-members are more likely to stay or become friends across time relative to actors who aren't in the same foci. Okay. All right, so that's the results I want to cover. Some next steps that one could take, probably estimate some additional models. One would be to get a more parsimonious model, as I mentioned earlier. It would also be interesting to run some models to try to figure out why does this indirect homophily go away, right? We have people ending up in activities with people who are similar, and it doesn't appear to be a preference for that, a direct preference for that. So are there other effects that are indirectly leading to that pattern? We also want to test for goodness of fit, just like with one mode Santa models. Check that. We can estimate the relative influence. That's fun to do. It's a way to get kind of the equivalent of standardized effects, where we want to know how much, how much does each effect contribute to, the changes that we observe in the networks. And so there's an example in a paper in Social Networks from 2022 that does this. It's now built into our Sienna for TwoMode networks, making it much easier. I talk about it in more detail there, but this can kind of get a sense of, again, are certain kinds of selection mechanisms kind of more important in driving change than others. You may also be interested in decomposing the overlap of co-membership and friendship, right? So this is the kind of, when we're talking about selection influence, people often wonder, well, which is it more one or the other, right? And so using similar kinds of a simulation procedure, you can go through and see how much friendships lead to co-membership with and without effects of influence in the model versus co-membership driving friendship. So the paper by Fujimoto et al. In 2018 applies that to some data on friendship and sport participation coevolution. All right, here are a few studies. I do want to say briefly, the first one kind of really tries to identify the classes of mechanisms that are important in modeling two-mode networks, tries to provide some kind of a topology to help organize those and think about those. And it models strictly a two-mode network. Many of the other papers shown here model two-mode and one-mode networks, and in the case of the latter, actually multimodal networks. If you're interested in health, the second paper talks about health lifestyles, actually treats health lifestyles, adolescents' lifestyle membership as a mode. Okay, so we have friendships evolving and friends as actors in a two-mode network, and then friends are choosing, or actors, adolescents are choosing lifestyles, which is kind of a fun kind of use of the two-mode approach. Okay. All right, so that is the end of the lecture. I just want to show you briefly the, a second, here we go. All right, just want to show you briefly the script that was used to prepare these results, as well as some other kinds of just some other kind of things. I'm gonna go brief. Part one here sets up the data. So the data is a set of matrices and data frames that then get turned into Siena objects. And so you can walk through those steps here. We ultimately create two data sets. One is just the two-mode network, and one is the two-mode plus the one-mode. Remember, any dependent network that you put into a data set at this step, Siena is going to want you to model it, right? So we can't use this data set that includes membership and friendship if we just want to model friendship, or if we just want to model membership. We're going to get rate functions and out degree effects for the other one that, and so it's easiest just to create a data set with the outcomes that you want. Okay, we're saving that data set, and then in the second part, we are reading it in, setting up the quick two-mode or quick models for the two-mode network that just look at indirect homophily. Okay, then we're going to set up a fuller set of models, and here we go through the different kinds of effects that we want to include in each of these, and then estimate a series of models. We get some bad convergence along the way, and fix some parameters to try to account for that, and do some rerunning to improve our estimates. So we walk through that, get a reasonable converging model, although still not parsimonious. And then the third part brings in a two-mode and a one-mode network, and models their coevolution. We bring in a few sets of new effects for the one-mode network, largely keep the same two-mode effects, and then bring in the multiplex effects and estimate those. Okay. Again, there's a lot here. So you're better off working through it on your own. And I understand we will have a Q&A section. So if there are questions about modeling two-mode networks and setting up Siena models for two-mode networks, that's really where we'll get those more. We'll narrow in and on those questions that are outstanding. So. All right, I hope this has been helpful. Good luck in your modeling efforts. All right, take care.